So this is a quick presentation about my computational design work on some topic about the coming workshop. My name is Satoru Sugihara. I'm a principal of computational design studio ATLB. So I'm gonna quickly go through some of the computational design work I worked on in the past. I used to be a computational designer at Morphosis Architects in Los Angeles, and one of the projects I worked on is Fair Tower. That was a skyscraper project in Paris, and I worked on three areas of the project. One is diagram structure, another grading panelization, and then another one is the solar shading skin installed outside of grading. And then the skin was a stainless steel mesh. And then design process of the facade starts with testing tons of studies with different parameters. In this case, like testing horizontal panel, vertical panel, diagonal, etc. And once it sets certain direction, and then I also add some patterning on top of it. And then by changing parameters, any other pattern can be studied. And then I mostly worked on processing, and with certain coding structure, and you can kind of switch or swap certain module code or function and change the parameter, and then you can generate many variations quickly. And then another aspect of the design is that because this is a solar shading panel, so that needs to perform. So to optimize the performance, I develop a code to insert behavior of an agent in each panel, and so each panel try to find the highest solar location in front of that specific panel, and then calculate the angle of the highest altitude of the sun, which is actually always a summer solstice, and then try to maximize the cast shadow on the floor. So as a result, each panel is looking at different sun. So the south facade is checking the sun around the noon, and the east side is checking the morning sun, and the west side is in the afternoon. And about diagram structure, in a traditional way of making diagram is actually creating grid on four-sided surface. But if you have irregular boundary condition, it might not work. So in this case, I applied the particle simulation with tension as a mesh relaxation. But that relaxation creates the smoothest continuous diagram geometry, but that also means that each line or each column has unique length inside. So that's expensive. So to rationalize them for cost efficiency, so it goes through a bunch of processes. And the rationalization is mostly based on kind of mathematical or geometrical knowledge, and you just analyze by hand, not automated. But the stitching between each area is automated. So the gray area is applying is readjusted by the tension mesh relaxation algorithm. So when you remove those colors, you don't see the same. And another rationalization is on the grading panel. And initially it was panelized using the diagrid center lines, but later we found there's a way to panelize with the radial faceting. So to remove tiny triangular panel, which cannot be produced with a glass. So with radial faceting, you can replace those triangles with a rectangle or parallelogram or trapezoid. This project is Milan Expo China Pavilion in 2015. And the architect was a studio link arc, and I worked on a roof facade, which was made out of woven bamboo panel mounted on steel frame. And I joined the project from the completion phase. So And in the competition phase, everything is washed out in production, so geometry wasn't necessarily clean. But later, after we won the competition, I rationalized the geometry to have certain geometric efficiency later, which is actually just making, well, trying to maximize straight line and then flat plane and then arc instead of a free form curve. Then next step is to create a equally spaced grid, and then the geometry of panel was generated on the surface with zero tolerance, so with no gap, but this creates a maximum unique panel numbers. So then you panelize, or you unitize them by approximating those unique panels into certain units. And then in this case, most of the panel was bent like 5 times slightly, but by just approximating those panels into the no fold or 1 fold or maximum 2 fold, and then so as a result you can limit the variation of units. And you also need to rationalize the joint, and the joint can be fixed joint or universal joint, but each of them have defined a level of degree of freedom. And then in this case we have a certain offset from the joint location that was that's flexible, but the height of the unit joint is fixed, so we try to rationalize them or unitize them. But unitize them, it requires compromise the unitization of the panel, so there's a trade-off relationship between joint rationalization and the panel rationalization, so we just need to find the best balance between them. For that purpose, I externalized the data from my processing code, and so for other people to control my code. So that was up to architects and the consultant. If they think certain area needs to be in some specific way, they can adjust by changing the number of pixels. And then as a result, it was built in a best balance of efficiency and the quality of the building. This project is a common house in Singapore, but architect is Wow Architects. And then I worked on it's a punching metal grid, perforated metal grid with the tab coming out. So in this case, the architect had an idea to project certain tree image onto the perforated metal, and then produce in a metal fabrication facility. And so first I started with generating tree patterns because they are interested in certain kind of computationally generated tree patterns. But later, more kind of stronger constraints came in from the fabricator, who produced a perforation out of a limited set of die. So the type of hole we can use was limited. And so later the branch or the tree image was simplified, but I tried to manage the hole size, and also the extruded tab works as a solar shading louvers. So the orientation and angle can be controlled. So I built a Y set bunch of grayscale image to control the perforation hole size, and then extruded the tab angle and orientation. And everything was imported to processing, and they generate that processing generates 3D geometry and then 2D drawing information. And those drawing information in one file was separated into 180 files of DWG, and then sent to the fabricator. This project is Morphosis Emerson College Los Angeles Center. I worked on the courtyard facade. So this building is a combination with dormitory building and school, office, and classroom. So the central area has a courtyard, and which is public space, and then dormitory is a private space. So that this facade is separates them loosely and creatively, creating some kind of dynamic environment or atmosphere for the public area. and it's made out of folded aluminum sheet. And the initial idea was just create a certain system panel which slightly tweaked all over the area to create some kind of smooth field like effect. And initially we went through a bunch of studies, what kind of panel shape could be, or triangular panel, a folded panel, or rectangular panel, or how to layer them, or what kind of information to control the folding or spacing, etc. And then later, the layout system was switched to the particle simulation system, and because there's a tons of constraints like smoke debug or kind of like variation of the opening and closing. So the particle simulation was used as soft solver to satisfy all the constraints. And also, I mean, this the whole pattern seems to be smooth and continuous, but the panel types need to be limited to a certain number, and it was actually limited to 15 different panels, and then half of them are flipped. So the unfolded shape is just 8 different, which can perfectly fit within 4 feet by 8 feet aluminum sheet. Bill and Milan Gates Hall at Cornell University by Moses Architects. I worked on the facade. In this case, we knew we want to go rational. So we started with the module first, but I tried to build certain solar shading panel which creates the void shape more figural as well. So it's a ground figure issue. But the final one is made out of 10 different panels to create this open to close condition to create certain kind of dynamic move around the building. This finance city tower in Casablanca, Morocco was recently completed most of this project. And this facade is also similar approach, starting with the module and then studying in terms of different way, and which works best with the concept and then the design of the main building. So at the end, we went through kind of solid white diagonal louvers, and then with some random accents. This project is about a hot pot restaurant in China. This is the flagship store of the hot pot restaurant chain. And the architect is studying Clark and Ken AUD. And then that project started a bunch of studies, but towards the end we decided that certain kind of pattern, and I'm showing certain kind of rational logic of like dividing the ceiling in the grid and then creating certain variation. And at the end, with certain density differentiation, there's a 10 different panel module. And then that was installed into the ceiling. And then the material is a painted perforated aluminum sheet. And here I just speak about the software environment I use. So I use mostly processing, but also my own open source library. So that's kind of specialized in computational design and architecture. And with that, I mean, that can be used for panelization, kind of top-down panelization algorithm, but also for agent-based simulation. So like a swarm or certain growth algorithm that can be easily implemented on the environment. So those are just examples of, in this case, a swarm algorithm applied for certain kind of 2D graphic patterning. Those swarm algorithm creates certain kind of smooth flow geometry, but the one question is how you can use it in architecture. So to attack the problem, I worked on one installation by using those trajectory of swarm as a tensor structure. So to use those kind of free flow lines as a structure, there is a certain optimization needed. So just regular swarm simulation doesn't create any kind of sound structure. So there's a two different agent system. One is the swarm kind of particle system, and the second is a structure optimization system, which you can see left behind the swarm kind of node frame. So the movement above some kind of swaying movement is actually the optimization process of the structure to find the equilibrium in structure under gravity. And then with that optimization, this geometry can be built as designed under gravity. Similar approach was applied to another project, which was a certain conceptual project to build a pier in River Thames in London. And then I used a swarm simulation to create certain, again, the tensile structure out of complex trajectory geometry. But there's a one, so then the optimization, structure optimization applied to create a functional tensile structure with complex geometry. And this is my research about kind of cellular growth algorithm. So I was inspired by those mechanism in cell, how to grow their form out of embryo, and the simple simulation of like one node cell divided into two and then keep connection, or how to connect it. So it can create a bunch of different type of geometry. And then once I tried to apply this algorithm to a certain project, in this case an interior design project, collaborate with OR project. So this office installation was installed in the cafeteria in office space in Beijing. Then now a little bit about the coming workshop, and the theme is about the hierarchy in geometric order and agent behavior. So there's a certain issue these days that those agent approach I showed so far tends to show certain association with biological or natural geometry, and mostly because those algorithms was originally found in Nature in 70 in the research of complex science, and it's easily can be used to simulate those type of geometry in nature. But there's other type of geometry which is more kind of artificial or geometry artifacts, and then that doesn't need to be ignored. So to consider, or maybe there's a some other approach to deal with this type of geometry. And also the rays of the discourse about the discrete approach also gives spotlight on this issue. Although discrete is not only about going against biomimicry approach, it's also about the issue of construction, and then so that part I totally agree. But the period agent part, that issue, in my opinion, was not just simply that mimicking nature. I thought that's because of the certain way of application of random number, or like a lack of hierarchy or certain organization in the behavior. Because I mean that I'm guilty of that as well. But this conventional way of using swarm or certain growth algorithm is like a branching algorithm. That's kind of singular behavior, and then that should have more organization in behavior. So so I'm trying to kind of improve the agent behavior using more organized approach in behavior in time dimension. And my idea was not just abandon bottom up and going to top down. In my case, I tried to think about a hierarchy, but specifically in time dimension or in behavior. So actually, I thought of the body clock of agent. So usually body clock of agent is just singular clock, but what if that is stuck up? And then, for example, the one or like first order clock control the first order or behavior, but the second clock creates certain thing. Like for example, every second you do something, but every minute you do something else, and every hour you do something another behavior. So as a result, like there is a one agent creating a square, but another agent is branching, and yet another one is a branch of actually turning, and then there's a like a fourth level behavior is a branching again. And then, but anyway, so in this way, like you can stack up the behavior, and you can also control the behavior, like you have a control point or like a parameter in every level. So you, for this example, like a first order straight behavior was slightly tweaked, but the other behavior stays same. Or like yeah, this was another change of the angle, but you can insert the random behavior in different levels. So randomness doesn't come in the universal or singular level, uniform level, but randomness can be inserted in like hierarchical level. So that's the idea. And then I try to think of some like how we can compare this type of behavior as a result of this with the like a human artifacts aesthetics, and also even in nature. So even in actual nature, that's really hierarchical. Like insect body and the legs, and the body part, the head, all different. So that is a kind of things I want to work on in the workshop. So I look forward to have the workshop in the coming days, and I hope you can have a good experience there. Thank you.